dear students, it's me Vijay. So today I'm here with another important chapter, structure of atom. Now before getting into the chapter, first we have to learn about John Dalton. Who is John Dalton? John Dalton is the one, he's a chemist and he's the one who proposed atomic theory in the year 1808. So John Dalton is the one who proposed atomic theory in the year 1808, and his theory contained 6 postulates. One among those postulates is all the substance in the universe are made up of tiny particle called atom. So before getting into the chapter, first we have to learn about John Dalton. John Dalton is a chemist. He proposed a theory, and that theory is known as, it's a well-known theory, and that theory is known as John Dalton's atomic theory. That theory is known as John Dalton's atomic theory. I think already you have studied atomic theory in some basic concepts of chemistry. So you know the postulates of atomic theory. There are 6 postulates. This theory was proposed in the year 1808, and this theory consists of 6 postulates. I think already you know these postulates. You have already studied these postulates in some basic concepts of chemistry. 11th chapter 1. Okay, now according to this theory, according to John Dalton's atomic theory, there are 6 postulates. First postulate, one among those postulates is all the substance in the universe are made up of extremely tiny particle called atom. All the substance in the universe are made up of extremely tiny particle called atom. If you consider this substance is made up of so many tiny particle. That tiny particle, smallest tiny extremely small particle is known as atom. All the substance in the universe, if you consider this board is made up of so many tiny particles, and that smallest tiny particle is known as atom. Now if you consider this shirt is made up of so many tiny particles. That smallest tiny particle is known as atom. All the substance in the universe are made up of extremely tiny particle called atom. Atom is a Greek word meaning indivisible. Okay, so John Dalton in the year 1808, he proposed a theory. A theory is known as John Dalton atomic theory. The theory consists of 6 postulates, and one among those postulates is all the substance in the universe are made up of extremely tiny particle called atom. Atom is a Greek word meaning indivisible. Now, but later half of 19th century, that nearly 1850s, okay, in 1850s, that is later half of 19th century, through some experiments, some eminent scientists proved that atom can further divide it to smaller particle. This atom, the smallest particle, according to John Dalton, atom is the smallest particle, but in the year 1850, okay, later half of 19th century, some eminent scientists proved that atom can further divide it. Atom can further divide to smaller particles such as electrons, protons, neutrons, antineutrino, neutrinos, positrons, etc. So according to John Dalton, atom is the smallest particle. It cannot be further divided. But a later half of 19th century, exact year is 1850 to 1856, at that range, 1850 to 1856. So later half of 19th century, some good scientists, some eminent scientists proved that atom can further divide it to smaller particles like electron, proton, neutron, positron, neutrino, antineutrino, etc. Okay, I think it's clear. They can further divide into smaller particles like electron, proton, neutron, antineutrino, neutrino, positron, etc. mesons, etc. Okay. In this chapter, we are going to study in detail about electron, proton, neutron, and how these are arranged in an atom. How these particles are arranged in an atom. So in this chapter, we are going to study about electron, protons and neutron, how they are arranged inside an atom. Okay, I think it's clear. So by 1850s, some eminent scientists proved that atom can further divided into some smaller particles such as electrons, protons, neutrons, antineutrino, neutrinos, positrons, etc., etc. There are so many particles. These particles are known as subatomic particles. So atom can be divided into further divided into smaller particles such as electron, proton, neutron, positron, neutrino, antineutrino. There are so many particles. Those particles are known as subatomic particle present inside the atom. They are known as subatomic particle. Now, we are not concerned about positrons. We are not concerned about neutrino. We are not concerned about antineutrino. We are giving more importance, or we are concerned about only these three particles. These are the three important particles. So here in this chapter we are going to study about these three particles. We are going to giving more concern about these three particles. Okay, we are going to neglect all other subatomic particles. We are going to study about these three important subatomic particles. Particles are electron, protons and neutron. Okay, electron is the subatomic particle first discovered. And this electron was discovered by J.J. Thomson. So J.J. Thomson was the one who first discovered electron. And the experiment conducted by J.J. Thomson to discover electron is discharge tube experiment. So by discharge tube experiment, for the first time J.J. Thomson proved that atom can divide into electron. For the first time, by discharge tube experiment, J.J. Thomson proved that atom can divide into subatomic particle, and that subatomic particle discovered by J.J. Thomson is electron. Now the second subatomic particle discovered is proton. The second subatomic particle discovered after electron is proton. And this proton was discovered by Goldstein, and the experimental behind the discovery is discharge tube experiment. Again, discharge tube experiment. So by using discharge tube experiment, Goldstein discovered electron. Now, neutron was discovered by none other than James Chadwick, and the experimental technique or experiment behind the discovery of neutron is alpha ray bombardment with beryllium nucleus. Alpha ray is bombarded with beryllium nucleus, or alpha ray is collided with beryllium nucleus. This is how James Chadwick discovered electron. So in this chapter we are going to study in detail about the discovery of these particles and where they are present in an atom. I think it's clear. So electron was discovered by J.J. Thomson, and the experiment behind this discovery was discharge tube experiment. And proton discovered by Goldstein, and the experimental technique behind this discovery, discharge tube experiment. And neutron, neutron was discovered by James Chadwick, and the experimental technique behind this discovery is alpha ray bombardment with beryllium nucleus. I think it's clear. Moving on to next topic, discovery of electron. Now we know that electron was discovered by J.J. Thomson, and the experiment technique is discharge tube experiment. So we are going to study discharge tube experiment in detail. Now J.J. Thomson discovered electron by discharge tube experiment. And discharge tube experiment, what is discharge tube? Actually, what is discharge tube? A discharge tube consists of a glass tube. It's a long glass tube. A discharge tube consists of discharge tube experiment. So we are going to explain. We are going to describe discharge tube experiment. So a discharge tube consists of a long glass tube. And this glass tube is filled with a long glass tube, and this glass tube is filled with a gas at very low pressure. Gas under low pressure. So a discharge tube consists of a long glass tube. It's a glass tube, and this is filled with a gas under low pressure. Okay. Now there are the terminals of the two terminals of the glass tube contain two metal electrodes. Okay. Now a very high voltage, nearly around 10,000 volt, 10,000 or more than 10,000, 10,000 volt or more than 10,000. Okay, greater than or equal to 10,000. So, sorry, 10,000 or more than, more, okay. So, very high voltage is applied across this electrodes. So, a discharge tube contains a long glass tube, and this glass tube is filled with a gas. You can fill any gas, let it be helium or hydrogen or any gas. A gas is filled under low pressure in this glass tube, and these glass tube, at two ends of this glass tube there are two metal electrodes, and this metal electrode, to this metal electrode a very high voltage nearly 10,000 or more than 10,000 volt is applied across this electrode. Now this the negative terminal electrode, negative attached electrode is known as, this electrode is having negative charge, this electrode is known as, negative charge electrode is known as cathode, and positive charge is applied to this electrode. So this electrode is having positive charge, and this electrode is known as anode. Positive charge electrode is known as anode. Okay, now this experiment is conducted by J.J. Thomson by taking perforated anode, by taking not simple anode, but here J.J. Thomson took a perforated anode. He is not taking a simple anode, he is taking a perforated anode. What does mean by perforated anode? Perforated anode means if anode is having so many holes, okay, anode with holes, this electrode is known as perforated anode. Anode with holes, anode with holes. These type of electrodes are known as perforated anode. Perforated anode. So here a glass tube filled with gas at low pressure or under low pressure, a very high voltage is applied across the electrodes, and here negative applied electrode is known as cathode and positive applied electrode is known as anode. Now here J.J. Thomson is taking he took a perforated anode. He took a perforated anode. What does mean by perforated anode? Anode with so many holes. These anodes are known as perforated anode. Now just behind this perforated anode, he coated zinc sulphide. Zinc sulphide. He coated zinc sulphide. Zinc sulphide. Now zinc sulphide is a fluorescent substance. Zinc sulphide is a fluorescent substance. Any invisible radiation strikes on zinc sulphide, it will produce a flash of light. Okay, any invisible radiation, when it strikes on zinc sulphide, it will produce a flash of light. Okay, so this is discharge tube experiment. So here in discharge tube, so by discharge tube experiment, J.J. Thomson discovered electron. Now we are going to study about that discharge tube experiment. A discharge tube consists of a long glass tube, and it is filled with a gas under very low pressure, and a very high voltage is applied across the electrode fitted at the terminals of this glass tube. Now negative electrode is known as cathode and positive electrode is known as cathode. Now J.J. Thomson took not a simple anode, he took a perforated anode. Perforated anode means anode with so many holes. He took a perforated anode, and that anode, just behind that anode, perforated anode, he called zinc sulphide. Now what is the importance of zinc sulphide? Zinc sulphide is a fluorescent substance. Fluorescent substance. Any invisible radiation that is invisible to our eye, radiation which are invisible to our eye, any invisible radiation strikes on zinc sulphide, they will produce a flash of light. That flash of light is known as scintillation. Okay, they will produce a flash of light. When any invisible radiation strikes on zinc sulphide, they will produce a flash of light. You can see a flash of light here. Okay, these radiations are not visible, they are invisible radiation, but when they strikes on zinc sulphide, they will produce a scintillation, that is flash of light. So J.J. Thomson conducted this experiment. Now after conducting this experiment, what he was observing is that he is observing flash of light just behind this hole, just behind the holes of anode. Let this be the anode, and let this be the zinc sulphide. Let this be the zinc sulphide. Now what he is observing is that just behind this hole, he is showing flash of light in zinc sulphide. He is showing scintillation here. He is showing Scintillation means flash of light. Flash of light here. He is observing a flash of light here. That means just behind the holes of anode, okay, he is observing scintillation. That means some radiation is coming from cathode and it's moving towards anode. Okay, some radiation is coming from anode, some radiation is coming from anode and it's moving towards cathode. Sorry, some radiation is coming from cathode and it's moving towards anode. Okay, now here there is a vacant space. So this anode is passing through this perforated cathode and it is striking on the zinc sulphide. Okay, some radiation is coming from anode and it's moving towards anode. Now here in the space there is no anode, it is a hole. So this cathode ray pass through this hole and it strikes on zinc sulphide. Okay, pass through this, okay, strike on zinc sulphide. That is why he is getting scintillation or flash of light here. So by conducting this experiment, he observes that some radiation is coming from cathode and it's moving towards anode. Okay, this radiation, he called this radiation as cathode ray. He called this radiation as cathode ray. Radiation coming from cathode, and this cathode ray leads to the discovery of electron. This cathode ray, these are called cathode ray, and these cathode ray leads to the discovery of electron. So I'll explain this tube experiment once more. This tube experiment consists of a long glass tube filled with a gas under very low pressure, and the two ends of the glass tube is fitted with two electrodes, and a very high voltage is applied. Nearly 10,000 or more than 10,000 is applied across the electrode. Now he is not using a simple anode electrode. He is using a perforated anode. Now perforated anode means anode with so many holes. This is known as perforated anode. Now he is coating zinc sulphide just behind this perforated anode. Okay, now what is the importance of zinc sulphide? Zinc sulphide is a fluorescent substance. When some radiation which are invisible to our eyes, when they strikes on zinc sulphide, that zinc sulphide will produce a flash of light. Okay, that is the importance of zinc sulphide. It's a fluorescent substance. Now, after conducting this experiment, what he was observing is that he is observing scintillation or flash of light just behind these holes of anode. So he knows that some radiation is coming from cathode, and it's moving towards cathode. Since here there are vacant space are here, that is why this cathode ray, these radiation pass through this hole and striking on zinc sulphide. Since there is a vacant space, hole here, these cathode ray pass through these holes. Okay. So radiation coming from cathode and it's moving towards anode. These radiations are known as cathode ray. These radiations are known as cathode ray. I think it's clear. This is how electron is discovered. Cathode ray is discovered, and this cathode ray leads to the discovery of electron. This is how cathode ray is discovered, and this cathode ray leads to the discovery of electron. I think it's clear. Moving on to next topic, that is properties of cathode ray. Now properties of cathode ray was studied by J.J. Thomson by using the same old experiment, that is discharge tube experiment. So properties of cathode ray was studied by J.J. Thomson by using same discharge tube experiment. So we are going to study the properties of cathode ray. First property. Now, so again, a discharge tube, a glass tube filled with a gas at low pressure, gas under low pressure, and a very high voltage is applied across this electrodes. Okay, I think it's clear now. So for better understanding, I'm just expanding the back side of this, that is the anode side of this tattoo, to understand the property. So to understand the property, I am just extending the anode side. Okay, now let this be the discharge tube. Now here a gas is filled under low pressure and a very high voltage is applied across the electron, and here we are using perforated anode electrode. Here we are using perforated, not we. Here J.J. Thomson is using perforated anode, and here zinc sulphide is coated. Zinc sulphide is coated. Just behind this perforated anode, zinc sulphide is coated. So the same old discharge tube experiment. So a discharge tube is filled with a gas at very low pressure and a very high voltage. Very high voltage, that is nearly 10,000 or more than 10,000 volt is applied across this electrode. Here we are using perforated anode electrode. Cathode is normal cathode, but anode is perforated anode. Perforated anode. Okay. Now back side of the anode we are coating zinc sulphide. Now not we, J.J. Thomson is coating zinc sulphide. Now when he conduct this experiment, what he was observing is that he is getting scintillation just behind this hole. 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 He is not getting scintillation or a flash of light. Flash of light is also known as scintillation. So he is not getting scintillation anywhere else. He is only getting scintillation just behind this holes. So he is getting a flash of light, okay, just behind the holes of the anode. He is not getting flash of light anywhere else. Okay, that means this shows that anode ray, cathode ray, this is cathode and this is perforated anode. This is perforated anode. Okay, I know, I think it's clear. So here perforated anode is used. So he is getting scintillation just behind the holes. He is not getting scintillation anywhere else. So that means it shows that cathode ray travel from cathode to anode in a straight line. Cathode ray travel from cathode to anode in a straight line. It is only traveling in a straight line. If it travel in some other way, you will get scintillation here, 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 etc. But here we are getting only scintillation just behind these holes. This shows that cathode ray always travel in a straight line. So this is the first point. Cathode ray always travel in a straight line. Cathode ray travels from cathode to anode straight line. Cathode ray travel from cathode to anode in a straight line. I think it's clear. Here he placed zinc sulphide just behind the perforated anode, and when he conduct this experiment, he is observing that he is getting scintillation just behind the holes. He is not getting scintillation anywhere else. This shows that cathode ray always travel in a straight line. They are not traveling in like in a zigzag manner. If it's traveling in a zigzag manner, then you will get scintillation here, here, etc. But he is getting scintillation just behind the holes. This shows that cathode ray travel in a straight line. So this is the first property. Cathode ray travel from cathode to anode in a straight line. I think it's clear. I think it's clear. Now, second point. I think it's clear. Here, properties of cathode ray was discovered by J.J. Thomson by using the same experiment, discharge tube experiment. I am rubbing that heading, discharge tube experiment. Okay. Now, second property. He placed a positive charge plate and a negative charge plate in the path of this cathode ray. This is the cathode ray. He placed a positive charge plate and negative charge plate in the path of the cathode ray. Okay. So what he is observing is that initially he is getting scintillation just behind the holes of the cathode ray. But when we place a positive plate and negative plate, okay, when he places a positive plate and negative plate, instead of getting scintillation here, he is getting scintillation here. Scintillation means flash of light. Flash of light. It's a flash of light. Okay. So initially he got scintillation just behind the holes of the cathode ray, but when he placed a positive plate and negative plate, instead of getting scintillation here, he is getting scintillation here. Here near to this positive plate. This shows that cathode ray, one straight travel cathode ray, now it is deflected towards this side. That's why we are getting scintillation here. Okay. Initially the cathode ray travel in a straight line, but when we place a positive and negative plate, now the cathode ray is traveling, or it is deflecting towards positive plate. Now if somebody is deflecting towards positive side means then that they are negatively charged. If somebody is deflecting towards positive side means they are negatively charged. So the second point, second property is cathode rays are negatively charged particle. Cathode rays are negatively charged particle. Why they are negatively charged particle? Why they are negatively charged particle? Because they are deflected towards positive side. Cathode rays are deflected towards positive side, showing that they are negatively charged particle. I think it's clear. This is the second property of cathode ray. Okay. Moving on to third property. Now he plays a pinpoint wheel. Okay. Okay, this is anode. Okay. Now he plays a wheel. Wheel is a small wheel. That wheel is known as pinpoint wheel. He plays a small pinpoint wheel in the path of cathode ray. He plays a small pinpoint wheel in the path of cathode ray. This is pinpoint wheel. He placed a pinpoint wheel in the path of cathode ray. So what he was observing is that the pinpoint wheel, okay, it's moving from this end to this end. It's moving from this end to this end. Okay. He placed a pinpoint wheel. It's a small weightless wheel. He placed a small weightless pinpoint wheel in the path of cathode ray. So what he observes is that the pinpoint wheel is moving from this point to this point. It's moving from left side to right side. Okay. I think it's clear. And this shows that cathode ray consists of mass, or they are material particle. Cathode ray possesses mass because cathode ray is having mass. If something is having mass, then they have strength. If some particle is having mass, means they have strength. That is why when this cathode ray strikes on this pinpoint wheel rotates and it is moving from this point to this point. Okay, so cathode ray is having mass. So if a particle having mass, when it collides with a wheel, when a particle having mass, okay, mass means it possesses strength. So when a particle is having mass, it possesses some strength. When a particle having mass collide with this pinpoint wheel, it will rotate. Obviously it will rotate, right? For example, if you consider this pen. Okay, if you consider this pen, my hand is having mass, that means I'm having strength. So when I touch this pen, it's moving, right? So it shows that I'm having mass or strength. So particle having strength or particle having mass, when it collides with a pinpoint wheel, the wheel will rotate. This shows that cathode ray, particles of cathode ray are material particle. Cathode rays are material particle. Material particle means particle having mass. Material particle. Cathode rays are material particles. That means particles having mass. Particles having mass. I think it's clear. This is the fourth property. So first property, cathode ray travel from cathode to anode in a straight line. Second property, they are deflected towards positive plate, showing that they are negatively charged particle. Third point, they are material particle. Material particle means particle having mass. The pinpoint is moving from this to this end to this end. That means when this cathode ray collides with this pinpoint, it's moving. So the cathode ray should possess mass. If a particle is having mass, that means they have strength. That's why the pinpoint wheel is moving. So cathode rays are material particle. That means they possess mass. I think it's clear. Now fourth property. He changed the gas filled in the discharge tube. He changed the gas filled in the discharge tube. He first placed helium, then hydrogen, then neon, then nitrogen. He changed the gas filled in the discharge tube. He changed the electrode used. First he used iron, then zinc, then copper, etc. He changed the electrode used. So fourth property, J.J. Thomson changed the gas filled in the discharge tube. First he filled hydrogen. Then he removed hydrogen and filled helium. Then he removed helium and filled neon. He changed the gas filled in the discharge tube. And he changed the electrode used. Now what he is observing is that cathode ray, charge by mass ratio, charge by mass ratio, it is represented by E by M. Charge by mass ratio of cathode rays are independent of gas filled and electrode used. So he changed the gas filled in the discharge tube and electrode used. Irrespective of the nature of gas or electrode used, always charge by mass ratio of cathode ray remains same. Charge by mass ratio of cathode ray remains same. E by M ratio remains same. I'll explain once more. He changed the gas filled in the discharge tube. A gas is filled under low pressure. So he changed. In each time he changed the gas filled in the discharge tube. First he placed hydrogen, then he placed helium, then he placed neon, then he placed nitrogen. He changed the gas filled in the discharge tube. And also he changed the electrode used. First he used iron, then he used zinc, then he used copper. So he tried to change the electrode used. Irrespective of the nature of gas or electrode used, the charge by M ratio of cathode ray produced always remains same. He changed the gas and also he changed the electrode. Okay. Irrespective of the nature of gas and electrode used, the charge by mass ratio, that is E by M ratio, for a cathode ray always remains same. Always remains same. I think it's clear. So these are the 4 important postulate. Now we have to study two more points, properties, not postulate, properties. Now we have to study 2 more properties. I think it's clear. So last point, 4th one is he changed the gas filled in the discharge tube and he changed the electrode used. But charge by mass ratio, charge by mass or charge to mass ratio remains same for cathode ray irrespective of the nature of gas filled in the discharge tube and electrode used. I think it's clear. Moving on to next property. So 4th one. Moving on to 5th one. Okay, when this cathode ray strikes on heavy metals, like or hard metals such as copper, tungsten, etc. When the cathode ray strikes on heavy materials such as copper, tungsten, etc. When they strikes on these material, a new radiation is emitted. When they strikes on these metals, copper, tungsten, etc., a new radiation is emitted. That radiation is known as X-ray. So 5th point, cathode ray strikes on heavy metal such as copper, tungsten, etc., producing X-ray. 5th point. So when cathode ray strikes on heavy material or heavy substance like copper, tungsten, etc., when they strikes on these material, a new radiation is emitted. That radiation is known as X-ray. So 5 important properties. I think it's clear. Okay, moving on to next property. Cathode ray possess heating effect. Cathode ray possess heating effect when they strikes on thin metals. So when they strikes on thin metal, they produce heating effect. So when they strikes, I'll show you the, okay. When they strikes on thin metal, very thin metal, okay, when they strikes on very thin metal, a heating effect is observed. here. So these are the important properties of cathode ray. I think it's clear. So cathode ray travel from cathode to anode in a straight line. Cathode ray deflected towards positive side, showing that they are negatively charged particle. Now cathode ray are material particle, that means particle having mass. Cathode ray, charge by mass ratio of cathode ray are independent of the gas filled in the discharge tube and electrode used. Now, fifth point, cathode ray strikes on heavy metals, producing a new type of radiation known as X-ray. They produce heating effect when they strike on thin metals. So, these are some of the properties. There are so many properties for cathode ray, and these are some of the properties of cathode ray. I think it's clear. Moving on to next topic, some important values of cathode ray or electron. Okay, now cathode ray is actually electrons. Cathode rays are actually electrons. So some important values for cathode ray or electron. Now charge of electron. Charge of electron is 1.6 into 10 raised to minus 19 coulomb. Actually electrons are having negative charge. So you can write it as negative. You can either you can write a negative value here, negative, or 1.6 into 10 raised to minus 19 coulomb. Electron is having a negative charge. We know that. So electrons are having negative charge. So charge of electron, some important. So we are going to discuss about some important values of cathode ray or electrons. Actually cathode rays are known as electrons. Some important values for cathode rays or electron. Now first one is charge of cathode ray or electron. Charge of electron. Okay, charge of electron. Now charge, value of charge of electron is 1.6 into 10 raised to minus 19 coulomb. And the electrons are having a negative charge. And charge of electron was discovered by Robert A. Millikan, and the experiment used to discover the charge of electron is oil drop experiment. So Robert A. Millikan, by using oil drop experiment, he calculated the charge of electron, and charge of electron is 1.6 into 10 raised to minus 19 coulomb. 1.6 into 10 raised to minus 19 coulomb, and electron is having a negative charge. I think you know that. Now next one is mass. Mass of electron. Mass of electron is 9.1 into 10 raised to minus 31 kg. This is the mass of electron. So you have to remember these values. Mass of electron is 9.1 into 10 raised to minus 19 coulomb. Now next one is charge by mass. Charge divided by mass. Charge divided by mass. That is charge by mass. Charge by mass ratio. And charge by mass ratio value, you have to divide this value with this value. So charge by mass ratio of electron is 1.75882 into 10 raised to 11 coulomb per kg. 1.75882 into 10 raised to 11 coulomb per kg. And the charge by mass ratio of electron was discovered by J.J. Thomson by using the same experiment, discharge tube experiment. So you have to remember these values. So once more, charge of electron was discovered by Robert A. Millikan, and the experiment is oil drop experiment, and its value is charge of electron is 1.6 into 10 raised to minus 19 coulomb, and electrons are having a negative charge. Either you can write a negative, or without negative you can write the value, because we know that electrons are having a negative charge. Okay, now mass of electron. Mass of electron is 9.1 into 10 raised to minus 31 kg. Now next one is charge by mass ratio. Charge divided by mass. Charge by mass ratio, and value is 1.75882 into 10 raised to 11 coulomb per kg, and this value was discovered by J.J. Thomson by the same old experiment, that is discharge tube experiment. I think it's clear. These are the important values of an electron. I think it's clear. Moving on to next topic. Moving on to next topic, that is proton. Charge, mass and charge by mass ratio of proton. Now protons are also known as anode ray or canal ray. So charge, mass and charge by mass ratio of proton or anode ray or canal ray. Now charge of proton is same as that of charge of electron, but the only difference is protons are carrying positive charge. So charge of proton is similar to that of charge of electron, 1.6 into 10 raised to minus 19 coulomb. The only difference is in their charge. In the case of proton, they carry positive charge, whereas in the case of electron, they carry negative charge. Okay, so protons, charge of proton is 1.6 into 10 raised to minus 19 coulomb, and they are carrying positive charge. Now mass of proton is 1.67 into 10 raised to minus 27 kg. This is the mass of proton. This is the mass of proton. And charge by mass ratio of proton. Charge by mass ratio of proton is 9.58 into 10 raised to 7 coulomb per kg. So you have to remember these values. So charge of proton is similar to that of charge of electron. The only difference is in their sign. Protons are carrying, having 1.6 into 10 raised to minus 19 coulomb charge. The only difference, they are positive charge. Electrons are negative charge. Now masses are different. In the case of proton, masses 1.67 into 10 raised to minus 27 kg. And the charge by mass ratio of proton is equal to 9.58 into 10 raised to 7 coulomb per kg. So you have to remember charge, mass and charge by mass ratio of electrons and protons. I think it's clear. Moving on to next topic, that is discovery of proton. Now proton was discovered by Goldstein. Proton was discovered by Goldstein, proton or anode ray. Anode ray, discovery of anode ray. Actually anode rays are later known as protons. So discovery of anode ray. Now anode rays are discovered by Goldstein by the very same experiment, discharge tube experiment. Okay, later these anode rays are known as protons. So anode rays was discovered by Goldstein. Later these anode rays are known as proton, and the experiment used to discover anode rays are known as discharge tube experiments. Now here the same experiment which we have discussed earlier. So a discharge tube experiment consists of a glass tube fitted with 2 electrodes. Okay, now a gas is filled under low pressure. Gas under low pressure, or gas at low pressure. Gas at low pressure. A gas is filled under low pressure, and a very high voltage is applied across these electrodes. Okay, so a discharge tube consists of a glass tube filled with a gas under very low pressure, and a very high voltage is applied across the electrode. Okay, now this negative attached electrode is known as cathode, and positive attached electrode is known as anode. Now Goldstein conducted this experiment by using perforated cathode. He used perforated. Now what does mean by perforated cathode? Cathode having holes. So he conducted this experiment by using perforated cathode. That means this cathode is having holes. Okay, he conducted this experiment by using perforated cathode. Now just behind this perforated cathode he coated zinc sulphide. Now what is the importance of zinc sulphide? Zinc sulphide is a fluorescent substance. When some radiation strikes, when some invisible radiation strikes on zinc sulphide, it will produce a flash of light, and that flash of light is known as scintillation. So it will produce a scintillation. So when some invisible radiation strikes on zinc sulphide, you can see a flash of light. So zinc sulphide is a fluorescent substance. So here Goldstein used a discharge tube experiment to discover anode ray. Anode rays are protons. So a discharge tube experiment consists of a long glass tube fitted with 2 electrodes, and a gas under very low pressure is filled in this discharge tube, and a very high voltage is applied across this electrode, and here he used perforated cathode. Just behind this perforated cathode he coated zinc sulphide. Zinc sulphide is a fluorescent substance. When an invisible radiation strikes on zinc sulphide, it will produce scintillation. Now when he conducted this experiment, what he was observing is that he observed scintillation, that is flash of light, just behind the holes. Just behind these holes in zinc sulphide, he observed flash of light. So he understands some radiation is coming from anode and it's moving towards cathode. Some radiation is coming from anode and it's moving towards cathode. These radiation, he called these radiations as anode ray or canal ray. Anode ray or canal rays. Later these anode rays or canal rays are known as protons. So this is how protons were discovered. I think it's clear. Moving on to next topic, properties of anode ray. Already I have written the properties of anode ray. Now properties of anode ray was studied by conducting discharge tube experiment. So discharge tube experiment consists of a glass tube, okay, fitted with 2 electrodes, okay, and a gas at very low pressure. Gas at low pressure is filled. Gas under low pressure. Gas under low pressure is filled inside this discharge tube and a very high voltage is applied across the electrodes. Now here to explain we are using perforated cathode. Here we are using perforated cathode, and I am just expanding the cathode side to explain the reaction. To explain these properties, I am just expanding the back side, that is cathodic side. Now this side is coated with zinc sulphide. This side is coated with zinc sulphide. The side is coated with zinc sulphide. Okay, so a gas under very low pressure is filled in the discharge tube and a very high voltage is applied across the electrode, and we are using perforated cathode, and just behind the cathode we are coating zinc sulphide. And when he conducted this experiment, he observed actually I have to tell you one more thing. Actually the properties of anode ray was studied by J.J. Thomson. Anode ray, properties of anode ray was studied by J.J. Thomson. Okay, J.J. Thomson is the one who studied the properties of anode ray. You have to remember that point. Okay, now when he studied these properties, he took a discharge tube experiment. He conducted a discharge tube experiment using perforated cathode. Now when he conducted this experiment, what he was observing is that he observed flash of light just behind this holes. He observed flash of light here, flash of light here, flash of light here. He is not observing any flash of light, that is scintillation, anywhere else. He is observing scintillation or flash of light. That flash of light is known as scintillation just behind these holes. So that means anode ray travel from anode to cathode in a straight line. Anode ray travel from anode to cathode in a straight line. They travel from anode to cathode in a straight line. So this is the first property. Anode ray travel from anode to cathode in a straight line. I think it's clear. Like cathode ray, they also travel in a straight line. Now when a positive plate, so this property was studied by J.J. Thomson. So please remember that, okay, J.J. Thomson. Okay, now when a positive and a negative plate is applied in the path of cathode ray, when a positive and negative plate is applied on the path of cathode ray, what he was observing is that initially he observed scintillation here, but when he places a positive and a negative plate, he is observing scintillation in the negative side of the plate. That is, he is observing scintillation here. That means these cathode ray are deflected towards negative side. Okay, initially the cathode ray the scintillations or flash of light were observed just behind this holes, but when he placed a positive plate and a negative plate, the scintillations are observed near the negative plate. That means these anode ray, they are not cathode ray, anode ray, sorry. These anode rays, or they are also known as canal rays, C-A-N-A-L, canal rays or proton. These anode rays are deflected towards negative side, showing that they are positively charged particle. So they are positively charged particle because they are deflected towards negative side. That means they are positively charged particle. Okay, I think it's clear. Now, when we place a pinpoint wheel, a small wheel, which we have discussed earlier when we discussed cathode ray. When we place a pinpoint wheel in the path of anode ray, this pinpoint wheel is moving from this end to this end. Okay, it's moving. It's just rotating from this end to this end. Okay, it will collide and it's rotating from this end to the. That means anode ray are material particle. That means they possess mass. Material particle. They possess mass. They are material particle. Now, one important thing is the mass of the anode ray. The mass of they are material particle. That means they possess mass. That's why this pinpoint wheel is moving from this end to this end. Okay, they possess mass. Now the important point is the mass of the anode ray depends on the gas filled here. The mass of the anode ray depends on the gas filled here. Their masses varies with the gas filled in the discharge tube. Their masses, the mass of anode ray cathode ray, mass of cathode ray will not change with gas, but mass of anode ray changes with the gas filled in the discharge tube. So mass of anode ray changes with the gas filled in the discharge tube. So they are material particle, and the mass of the anode ray, these anode ray, mass of these anode ray, their mass changes with the gas filled in the discharge tube. I think it's clear. You have to remember that point. And last and final point, charge by mass ratio. E by M means it's charge by mass ratio. E by M means charge by mass. Charge by mass ratio value depends on the gas filled in the discharge tube, because this is charge by mass. Charge by mass. Actually, mass varies with the gas. Mass varies with the gas. We already discussed in third point. Mass varies with the gas. So their charge by mass ratio also varies with the gas. Okay, so charge by mass ratio depends on the gas filled in the discharge tube. Charge by mass ratio depends on the gas filled in the discharge tube. So these are the properties of anode ray. Now, I have to add one more point. I think it's clear. I think these points are clear. So, anode ray travel from anode to cathode in a straight line. They are positively charged because they are deflected towards negative plate. Now, they are material particle, but the mass of the anode ray depends on the gas. With gas, the mass will vary. Now, last point, charge by mass ratio value also depends on the gas filled, because charge by mass varies with the gas. So, obviously, charge by mass ratio value will vary with the gas filled in the discharge tube. I think it's clear. I think it's clear. Now, charge by mass ratio is maximum. Charge by mass ratio is maximum when hydrogen gas is filled. Charge by mass ratio is maximum when hydrogen gas is filled, because hydrogen is having the lowest mass. So mass value is lowest for hydrogen. Okay, hydrogen is the lightest gas known, so it is having the lowest mass. So mass decreases means charge by mass ratio value will be maximum. So charge by mass ratio for anode ray is maximum if we fill hydrogen gas in the discharge tube. If we fill hydrogen gas in the discharge tube, charge by mass ratio will be maximum. I think it's clear. I think it's clear. These are the properties of anode rays. Moving on to next topic, discovery of neutron. Now, neutron was discovered by James Chadwick. Neutron was discovered by James Chadwick, and he discovered neutron by bombarding beryllium nucleus with alpha rays. Alpha rays, beryllium nucleus with alpha rays. He discovered neutron by bombarding beryllium nucleus with alpha rays. Now, always you have to remember one thing. Alpha rays is similar to helium nucleus. Alpha rays is similar to helium nucleus. So instead of alpha rays, we can write helium nucleus. Alpha rays similar to, mass of alpha rays similar to helium nucleus. So instead of alpha ray, you can write helium nucleus. Okay, mass of alpha rays similar to helium nucleus. So he bombarded beryllium nucleus with alpha rays. So he got carbon and one chargeless particle. One chargeless particle. This chargeless particle is known as neutron. So neutron was discovered by James Chadwick, and his experiment was he bombarded beryllium nucleus with alpha rays. Now, mass of alpha ray is similar to that of helium nucleus. So instead of alpha ray, you can write helium nucleus. So when this helium nucleus collide with beryllium, 4 plus 2, you will get 6. 6 is carbon. 6 carbon, 12. 9 plus 4 is 13. Actually, 9 plus 4 is 13. Here it's only 12. So one mass is there. One mass 0. Here it's 0. 4 plus 2, 6. Here also 6. So remaining 0. 9 plus 4, 13. Here 12. So 1. So we got a chargeless particle. This chargeless particle is known as neutron. This is how neutron was discovered. Now, important values for neutron. Important values. Charge, mass and charge by mass ratio of neutron. Charge, mass and charge by mass ratio of neutron. So neutron was discovered by James Chadwick. He bombarded beryllium nucleus with alpha rays. So he got carbon and a chargeless particle, neutron. Now, important values of neutron. Neutron. Now, charge, mass, charge by mass ratio. Charge of neutron is 0 because neutron is a chargeless particle. It's a chargeless particle. So, charge of neutron is 0. Now, mass of neutron is similar to mass of proton. So, it is 1.67 into 10 raised to minus 27 kg. Mass of neutron is similar to that of mass of proton. That is 1.67 into 10 raised to minus 27 kg. 1.67 into 10 raised to minus 27 kg. Similar to that of proton. Now, charge by mass ratio. 0 by this value. So, we will get 0. So, these are the important values of neutron. So, we learned charge, mass and charge by mass ratio of electron, proton, neutron. You have to remember all the values. You have to remember all the values for all the subatomic particles. I think it's clear. Moving on to next topic, atomic number and mass number. Atomic number and mass number. Now, atomic number is represented by Z and mass number represented by A. So, atomic number and mass number. Atomic number is represented by Z and mass number is represented by A. Now, what is atomic number? Atomic number is the number of protons or number of electrons in an atom. It's a number of protons or number of electron in an atom. Atomic number is the number of protons or number of electron in an atom. Now, what is mass number? Mass number is the sum of number of protons and number of neutrons in a nucleus. So, it is the sum of number of protons and number of neutrons inside a nucleus. Okay, so you should remember these two, atomic number and mass number. Atomic number means it is represented by Z. Atomic number represented by Z. It is the sum of, atomic number is the number of protons or number of electrons in an atom. Now, mass number means it is represented by A. It is the sum of number of protons and number of neutrons in the nucleus. In the nucleus of an atom. Okay. Now, number of neutrons, you can calculate number of neutrons if you know atomic number and mass number. Number of neutrons is calculated from atomic number and mass number by using this formula. Number of neutrons is equal to mass number minus atomic number. Mass number minus atomic number. So, you have to remember these three. These three are very, very, very important. So, what is atomic number? Represented by Z. It is the number of protons or number of electrons in an atom. Now, what is mass number? Represented by A. It is the sum of number of protons and number of neutrons in the nucleus of an atom. Now, you can calculate number of neutron from, if you know atomic number and mass number. Number of neutron is equal to mass number minus atomic number. Mass number minus atomic number. I think it's clear. Now, next topic is representation of an element. Representation of an element. Now, always elements are represented. Representation of an element. Always elements are represented like this. Representation of an element. Representation of an element. Okay, now let the element be X. Always atomic number is written left side as subscript, and mass number is written as in the left side as superscript. So, subscript and superscript, that is atomic number. This is the element X. Let X be the element. X means it is the element. Z means atomic number, and A means mass number. So, always atomic number is represented in the left side as subscript, and mass number is represented as in right side as superscript. Or otherwise you can represent like this also. Element Z here, atomic number here and mass number here. These two, you can represent an element and its atomic number and mass number by these two methods. Either you can write atomic number and mass number as subscript and superscript in the left side, or you can write atomic number as subscript in the left side and mass number as superscript in the right side. Okay, for example, if you consider oxygen, atomic number of oxygen, it is 8, mass number 16. 88O16. Atomic number 8, mass number 16. Now if you consider, for example, if you consider, you can consider any compound. If you consider nitrogen, atom number 7, mass number 14. Right? So, you can represent like this. Now carbon, C6, 12. Atom number 6, mass number 12. So this is how we represent an element. I think it's clear. I think it's clear. I think it's clear. Moving on to next topic. Moving on to next topic. Moving on to next topic. Isotopes, isobars and isotones. Moving on to next topic. Isotopes, isobars and isotones. Isotopes, tops, isobars and isotones. Isotopes, isobars and isotones. I'll start with isotopes. Now what are isotopes? Isotopes. What are isotopes? I'll write two examples. Isotopes. Example. 1H1, 1H2, 1H3. Example 1. Example 2. 6C12, 6C13, 6C14. Now these are isotopes. If you consider example 1, these are isotopes. Now they have same atomic number. If you refer this, they have same atomic number. This is atomic number 1, 1, 1. So same atomic number, but they have different mass number. 1, 2, 3. Different mass number, right? Different mass number. So atoms of same element, hydrogen, 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 same element. So they have same element. So I'm writing here atoms of same element, atoms of same element having same atomic number, different mass number, right? If you consider these three, they have same element, atoms of same element, hydrogen, hydrogen, hydrogen. They have same atomic number, but different mass number. These are isotopes. So atoms of same element having same atomic number, different mass number. If you consider this, atoms of same element, carbon, 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 atoms of same element having same atomic number, 6, 6, 6, having same atomic number but different mass number. These are known as isotopes. I think it's clear. I think it's clear. Now, next one is isobars. Now, what are isobars? Just opposite to isotopes. Isotopes, just opposite to isotopes are isobars. Now, what are isobars? Example 1. 6C14, 7C, 7 and 14, sorry. Now, example 2. One is enough, right? One example is enough. I will explain from here itself. Now, carbon, nitrogen. So, atoms of different element. Atoms of different element having different atomic number. Atomic number is different. Having different atomic number, but their mass numbers are the same. Their mass numbers are same. Atomic number, but same mass number. These are isobars. Atoms of different element. Atoms of different element having different atomic number but same mass number. Atoms of different element having different atomic number, same atomic mass. I think it's clear. Isotopes are atoms of same element having same atomic number, different mass number. Now isobars are atoms of different element having different atomic number but same mass number. I think these 2 points are clear. Moving on to last one, isotones. 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 Yeah, isotones. Now what are isotones? Isotones, example, 6C14, 8 oxygen 16. Now what are isotones? Atoms of different element, the carbon, oxygen, different element having different atomic number and different mass number. Different atomic number and different mass number. Different mass number. ERENT, different mass number. Atoms of different element having different atomic number and different mass number, but same number of neutron. Same number of neutron. How to calculate neutron? Number of neutron. Neutron is calculated using this formula. I think you remember mass number minus atomic number. Right. Now what is the number of neutron in this case? 14 minus 6 which is equal to 8. Now what is the mass number in this case? 16 minus 8 is equal to 8, right? So they have different atoms of different element having different atomic number, different mass number, but same number of neutron. Same number of neutron. Same number of neutron. So same number of neutron. These are known as isotones. I think these three topics are clear. Moving on to next topic.